Hi everyone. Now let's just solve 2-3 questions. So these questions are good. Just pause this video before solving it. Before seeing the solution. So pause this video, try it out. Just let me know whether A is the correct answer or B is the correct answer. So what they're asking is that if B is a linear combination of columns of A, okay. I'm not writing the whole question. So basically, they are talking about Ax equal to B. Now they are saying if this B is a linear combination of columns of A, then there is always a solution of Ax equal to B, or there is never a solution of Ax equal to B. Which means they are saying that this B on the right hand side is given to you, okay, which is a linear combination of columns of A. See, whenever I say solution, it means they're asking about the value of X. They're always given A, they're always given B. Now what they're saying is that A is given to you. Let me just take some A, maybe 1, 2, 3, and maybe let me just say 2, 3, 5, and let's suppose this is 3, 7, 6, something, okay. And then this X is unknown to me, and then they are saying this B is actually a linear combination of columns of A. This is given to me, which means what? That this B might be some linear combination. Let me take some linear combination. Let me take some B just for the sake of this question. So it is 6, 10 and 2, 12, let me say, and then 11 and 3, 14, right? Let's just say that this is B. I'm just taking one example that satisfies the given condition, which is the B is a linear combination of columns of A. Now they are saying that does this X exist? Do you have X or not? So which means, can you always find the solution, or you can never find the solution if B is a linear combination of columns of A? So see here that if B is a linear combination of columns of A, then you will always be finding the solution. Reason being is that since they have given that this is a linear combination of columns of A, which means what? It means that there exists some linear combination. So in this currently case that you know that 1, 1, 1 is the answer. But in general, you know that if that's the linear combination of columns of A, then whatever is the coefficient, you can write those coefficients here. In this case, 1, 1, 1 is the answer, right? If B is a linear combination of columns of A, then there is always a solution. Okay. So let's just do this question with more analysis. Suppose I have some matrix which is, let's suppose 1, 2, 3. Let's suppose there is a matrix and 3, 6, 9, 2, 4, 6, and there is some B which is suppose that 4, 7 and something like this, okay. 4, 7, 4, 7, you can take anything. Let me just say 12. So suppose this is B, this is A, and this is B. Now they're asking whether do you have X or not here, right? You have X or not. Now first of all, let's just check. Intuitively I'm just asking, so there is nothing mathematics going on here. Currently we are in the topic where we are saying that we are understanding this Ax equal to B intuitively, complete intuition, okay. There is no mathematics, which means there is no equation solving, there is no nothing like this, just an intuition. So suppose that they give you this B, they say this is A, and suppose they also say that this B is not a linear combination of columns of A. As you can also verify that, see, there is only one column. 1, 2, 3 is only relevant. These are the useless columns. Useless in the sense, these are the redundant columns. Whatever you can do with 1, 2, 3, you can do with all of this, right? Vice versa. Whatever you can do with all of this, you can do just with 1, 2, 3, because these are just redundant columns, right? So you can just remove these columns. It is like that. These columns are not adding any value to this A. So you can directly check whether these two vectors are a linear combination of each other or not, linearly dependent columns or not. So just see this 1, 2, 3. If you multiply, let's suppose by 4, then you cannot get this column, because here is 7, and for the if you multiply by the 4, you will be getting 8, right? So basically, you can say that this B, actually it is given. So let me write the particular question. They are saying that this is A, this is B, and they also give you. You don't need to verify. They give you, given that B is not a linear combination of columns of A. Okay, let's say that this is given to us. This is the question. Now what they're asking is that do you have a solution? Which means that there is a solution, which means that X exists or not. Let's suppose this is the question. This is a complete question that they have given to you. Then what do you think? See, if B is not a linear combination of columns of A, which means you cannot generate this B using these linear combination, then obviously there is no X exists such that you can get this B. because if x exists, then it means like if you multiply this a into x, then you will be getting a linear combination of columns of a. That's what we have been seeing since now, right? So if you multiply this, whatever the x exists, then if you multiply this ax, then it will be a linear combination of columns of a. Whatever you will be getting as ax, it will be just a linearly dependent on columns of a. But on the right hand side, you have something which is actually from another planet. What I mean to say that basically, let's suppose this columns of A are in one planet. One they are actually okay. In technical terms, they are actually spanning one vector space. But on the right hand side, that is given to you B, which is actually not lying on that same vector space that columns of A are actually spanning. Okay. Anyway, just cut this down. No need to worry about the span, vector space, these things are just a master level thing. When you go to IIT and ISC, you will get to know these things. For the GATE, it's completely useless thing. That's why I'm not telling you again. Okay. So okay, coming back to the question. Now, if this B is not a linear combination of columns of A, which means that it is given, right? If you cannot get this B as a linear combination of columns of A, that's why this X does not exist. So do you have the solution? Then answer is never ever, right? Answer is not just no. Answer is basically, like you can say no, but the feeling is like that, never ever. If B is not a linear combination of A, then you can never ever get the solution. So let me just write it here. If B is, here, particularly here, you try whatever hard you want to try. Whatever you write here, you cannot get this B, because whatever you will be writing here, ultimately it will be a multiplication of ax, right? A into x. Then it will be a linear combination of columns of A. You cannot get this B. How hard you try does not matter at all. Okay? You cannot get this B. Using any x, how hard you try does not matter at all. So basically, if B is not a linear combination of columns of A, then we cannot get a solution. We cannot get, let me just write in the naive way, and then it does not matter how hard you try. Okay, then it does not matter how hard you try, you can never get the solution. Right? So this is for sure. If B is not a linear combination of columns of A, then you can never ever get the solution, how hard you try. Similarly, on the other end, I can say if B is a linear combination of columns of A, then you will always get the solution, basically, right? Then you can say you will always get the solution. So it depends on B. It depends on B and A. Basically, if B is a linear combination of columns of A, then you will always get the solution. For example, in this case, it is a linear combination of columns of A, then you just write the coefficients, right? If it is not a linear combination of columns of A, it means it is from the another planet. How can you get it from this planet, right? Whatever right hand side you are writing, it is just like, this B is a child, right? B is a child of A. If this is from another planet, then how can you have this as a child? Like this. I don't know if I'm making any sense or not, but yeah. So this B is just a child of A, which means like it is just a byproduct of A. So basically, it is just one of them. It is just linearly dependent on this columns of A, right? Whatever this B is, it's just a linearly dependent columns just a linear combination of columns of A. If you are saying that you are writing a random B, which cannot be obtained from the linear combination of columns of A, does not matter how hard you try, you cannot get any X which can satisfy this equation. So here there is no solution. Okay, and if B is a linear combination of columns of A, then you will always get the solution, right? So these two facts should be clear to everyone. If there is any doubt, you can just let me know in the comments. So just see here that if B is a linear combination of columns of A, there is always a solution. If B is, at the same time, I can say If B is not a linear combination of columns of A, then there is never a solution. Okay. Yeah, just a second. So let me just paste this question also. If B is, I can say B is not a linear combination of columns of A, not a linear combination of columns of A, then there is never a solution. Right? I hope you understood this. Cool. So these are the two questions that I wanted to discuss. Now let's just solve one more question and one or two more questions. Okay. Let's solve this question. This is even a little bit tougher than the previous question. So what they are saying is that A is given to you, which is M cross N matrix. Okay, which means there are M rows and N columns. Which means that if there are M rows, then each column is basically in Rm, right? And number of columns are actually N because there are N columns. Now they are saying has M linearly independent columns. So if that M and N is confusing to you, let me just take the numbers. So I hope 3 into 5 is fine, or maybe yeah, 3 into 4, 3 into 5, something like this. Okay, let's suppose that A is 3 into 4, which means there are 3 rows and 4 columns, which means 3 rows means 1, 2, 3 rows, right? Which means every column is in R3. And now on top of that, they have given one more thing. They are saying that that it has M linearly independent columns. So it is M cross N, which means M linearly independent columns means what? That you are having 3 linearly independent columns. So ultimately there are 4 columns. I mean, in this way, in this terminology, there are N columns ultimately. But out of these 4 columns, they are saying that 3 columns are linearly independent. Actually, if I tell you truth, then in R3, if you are getting 3 columns linearly independent, I don't think you need anything else from this world. I mean, you are the most richest person. If you are getting 3 linearly independent columns in R3, right? Then what else you need? You can generate the entire R3. Okay, let's just see this question. What they're saying? They're saying that in R3 you have 3 linearly independent columns. Then there is always a solution. There is never a solution. There may or may not be a solution of X equal to B. So just pause this video and just let me know what is the answer you are getting. Okay, cool. Now let me solve this question. They are saying that in R3 you have 3 linearly independent columns. So let me just write it here. Maybe I can just do this one. Yeah. So this is a matrix which is of 3 into 4, where you have 4 columns, 1, 2, 3, 4, and you have out of these 4 columns, it is given actually. It is given that they are saying that M linear independent columns, which means out of these 4 columns, you have 3 linear independent columns. So obviously, I mean, this should be 3 into 4. This cannot be 3 into 2. If it is, I mean, this cannot be just 2 columns, okay? Because if this is just 2 columns, the given condition itself is not satisfied that you have 3 linearly independent columns. If the total columns is just 4 or just 2. Anyway, we need to satisfy the condition that is given in the question. So they are saying that you have 3 linearly independent columns in R3. In R3, you have 3 linearly independent columns. Now, you have some X here. I mean, you need to find the X, and you have some B here. This is A. Now, what they are saying that whatever A you take, you have R3. In the R3, you have 3 linearly independent columns, and you take whatever A you want, right? Now, for any B, I mean, there is always a solution for Ax equal to B means for any B, do you have the solution? See, this B will be a linear combination of columns of A. Since you have R3 and you have 3 linear independent columns, you can actually generate any B. You give me whatever B you want to give me, I will give you the coefficients. I will give you these coefficients because I am damn confident that I can find the coefficients because I have 3 linearly independent columns in R3, right? So for example, let me just give you the example. Let's suppose I have these 3 linearly independent columns, okay, which is 1, 0, 0. I mean, these are the convenient vectors because finding the coefficients is very easy to me, but you can take any other vector. But just for the sake of my selfishness, which means like I do not have to worry about the calculation and all, that's why I'm having these kind of vectors. Let's just have one more vector, anything, 2, 3, 2, minus 9, anything, okay. And then this is just X, then there is a B, which is whatever of your choice. You just give me any B. I will give you the options. You give me any B. Try giving me out. Let's suppose 37. Okay, 37 minus 52 790. Let's suppose you give me some complicated B, and then you think that I cannot produce the solution. Do you really think so? No, I can definitely produce this solution. 37 minus 52 790, and I don't need actually this column, so I just need to put the 0 here. Okay, isn't it? You give me any B, I will give you the solution, because I have 3 linearly independent columns in R3. So there is always a solution, right? I hope you understood. So there is always a solution. Maybe I can just, I can just go to this page. So I can say there is always a solution. The reason being is that I can produce coefficients for any B. So here the answer is, let me mark the answer here. There is always a solution, right? Okay. Now let's just see the same question in I think negation way, which means if A m cross n does not have, okay, earlier I was saying it has m linearly independent columns. Now let's suppose it does not have m linearly independent columns, which means let me take the similar example, which means you have 3 by 4, A is 3 by 4, and you have 4 columns here that I completely agree with you. But in the question they are saying, although you have the 4 columns, but you do not have 3 linearly independent columns. Let's suppose only these 2 are linearly independent. These 2 are actually not linearly independent, which means these are dependent on these 2 only. Which means total there are only 2 linearly independent columns. So that's what it is given me in the question, right? Now they are saying, do you always have the solution? Do you never have the solution? You may or may not have the solution. So yeah, that's very interesting question. Just think about it. So let me just give you the hint, and then maybe you can think about it more. So this is very nice question. Just try and let me know what is the answer you are getting. See, here what I'm saying is that you have this A, you have this X that you want to actually find out, and there is a B. Suppose, for example, I take some A, which is maybe, let's suppose 1, 2, 3, any A which is only having 2 linearly independent columns, and let's suppose this is 2, 4 and 5, something like this, and remaining 2 I am taking linearly dependent, because that's what given me in the question. So let's suppose this is 3, 6, 8. I mean just a linear combination, just a summation of these 2, and maybe I can say this is just maybe 2, 4, 5 again, or maybe, I mean, you can take any 2 columns which are actually not a linearly independent on these 2. So basically, if you just see, then only these 2 are linearly independent, rest are linearly dependent. So you can say that only 2 columns are linearly independent here, and which satisfy the given condition, where they are saying that in 3 by 4 you just have less than 3. I mean, you do not have you do not have m linearly independent columns, which means in R3 you do not have 3 linearly independent columns, which means let's suppose you have either 2, either 1, something like this, right? So let's suppose you have only these 2 linearly independent columns. Now tell me, for any B, do you have solution? Just think about it. Do you have solution for any B? Let's suppose I have a B here, which is let's suppose 1, 2, 3. Do you have the solution for 1, 2, 3? Just let me know. What do you think? See, if you put the coefficients, which is 1, 0, I mean, you are just bringing this, copying this, right? If you are just copying this, you can have the solution, which is this. You definitely have the solution. If you are just copying one of the vector, you definitely have the solution. So my question was, do you always have the solution or not? Like here, so I have given you one example where you are having the solution, right? See, here you are having the solution, which is 1, 0, 0, 0. But let's just take another example. Let's just say, do you always have the solution? Suppose I have some B, which is actually, instead of 1, 2, 3, I just say this is, let's suppose 4, 8, 10. Do you have the solution? Just let me know. Maybe you can say it is just 2 times of this. It is just 2 times of this. So that is why you will say this is, you don't take this, just take 2 times of this, and then this is why this is the solution that you will be getting, right? Okay, great. So it seems like that we have the solution. But my question is still same. Do you always have the solution? See, you have the solution is okay, but can you guarantee that for every B you will be having the solution? Which means, suppose if I take another B, okay, if I take another B, maybe something which is actually not dependent on these 2. Maybe let me just try taking it. Actually, I'm not sure if it will be linearly independent, but yeah, let's suppose it is 7. Actually, I'm not sure until and unless I verify. I'm not sure if it is from another planet, which means like I just tried my best by summing this out 3, 6, and then I tried differing out this at this particular index, but I'm not sure actually. Like, I mean, that's not the way to do it for more than 2 columns. Anyway, let's suppose this 3, 6, 7 cannot be obtained by these 2 columns. Okay, suppose, I mean, this is independent of these 2. Now, since out of these 4 columns, only 2 columns are linearly independent, which means these 2 columns are useless, completely useless. These 2 columns are actually completely useless because these 2 columns can be produced by these 2 columns. So that's why these 2 columns are completely useless. I never ever have to take, okay, in any solution, if I have the solution, I never ever have to take these 2 columns into the consideration. Whatever I can produce from these 2 columns is can be produced, I mean, vice versa. Whatever can be produced from these 4 columns can be produced using these 2 columns. These 2 columns are redundant, and I can always have the solution which is actually having 0, 0 here. I don't need these 2 columns. I mean, if you want, you can take it, but you don't need it. Anyway, coming to this question, if you have 3, 6, 7 here, suppose this 3, 6, 7 cannot be obtained from these 2. Can you have something here? Can you have something here? Since it cannot be obtained from these 2, how hard you try does not matter. See, again, that's the similar story, that this column is not a linear combination of these 2 columns, right? Or these 4 columns. Since this column is not a linear combination, suppose this column is not a linear combination of these 4 columns, then it does not matter how hard you try, you cannot have the solution. See, in R3 you just have 2 linearly independent columns, right? Okay. Now this column, if this column is a linear combination of these 2 columns, then you have the solution. But if this column is not a linear combination of these 2 columns, then you do not have the solution, right? The solution may or may not exist. That's my point. So you will say that this column here is not a linear combination of columns of A. That's why there is no solution. So in this case, I am saying that if you are having some A which is having, let's suppose, less than 3, maybe just 2 linearly independent columns, then it will depend on the B. If this B is a linear combination of these 2 columns, maybe you are just copying out. That's good. You are just doubling it out. That's good. Okay. But if if this is a linear combination of columns of A, then you have the solution. If that is not a linear combination of columns of A, you do not have the solution. Now you may ask me the question that why I was not having the similar story here. Why I'm saying that always a solution here. Why I'm not saying that, okay, what if this B is not a linear combination of columns of A? What if this B is a linear combination of columns of A? Why I'm not having these kind of arguments here? Because the second argument where I'm saying that B is not a linear combination of columns of A does not even exist. Because I am rich enough to get any B. So B has to be linear combination of columns of A, because I have 3 linearly independent columns in A. That is why I will say that for any B, I will be having the solution. Right? Here I always have the solution because I am the king of this world. Here in this case. Why? King or queen. Okay, whatever you prefer. So here in this case, why I am saying so? Because here in R3 I have 3 linearly independent columns. So my life is set. You give me any B, I will give you the coefficient. But in R3, if I have 2 linearly independent columns, just 1 linearly independent columns, then it will depend whether my capabilities are now limited actually. Okay. Now it will depend on B. See, if they say that does not have M linearly independent columns, which means like maybe 2, maybe 1, then my capabilities are limited. Then it depends on B. If B is a linear combination of columns of A, I'm just copying out one of the vector, then definitely I have the solution. I'm copying out this vector, definitely I have the solution. But if I'm having some vector which is beyond my capability, because my capabilities are now limited, not limitless. Earlier my capabilities were limitless because I was the king, but here my capabilities are very limited because here in R3 I just have 2 linearly independent columns. I hope this is clear. I'm sorry if I'm making it complicated, but I wanted to convey this really hard. Okay, I mean, I cannot skip this thing. Even though I want, but I cannot skip this thing. So I hope you understood. Actually, it's a nice concept. It's a easy concept also. After so much of exercise, I hope you understood this, right? Cool. So these questions are some conceptual questions which are really nice. I hope you understood. Now I have just done what? I have just converted that question into just a flow chart where I'm saying if Ax equal to B has m linearly independent columns, I mean if the answer is yes, which means in R3 you have 3 linearly independent columns, you are the king, you always have the solution. If no, then it will depend on the B. If no, then it depends on the B, whether this B is basically you're copying out one of the vector, you are doubling out, you are taking the linear combination. It depends on the B basically. If B is beyond my capability or in my capability, but here I am the king, so everything is in my capability basically. Okay, cool. So it's just a question that I have just converted in the flowchart. I mean, otherwise that's not necessary to even see this flowchart. I mean, this flowchart is correct, but it's not necessary to write it since we have covered it. Okay, cool. Again, this is again the next flowchart that I have, where I just I'm just having the first question as a flowchart, where I'm saying that if B is a linear combination of columns of A, then always a solution, right? Always a solution. If no, then does not matter how hard you try, never a solution. So it is as simple as that. Yeah, now solution can be unique, can be infinite. That is one thing, right? Okay, so till now, I hope these were the two questions that we covered, and I hope that's fine to everyone. Now I want to extend this idea a little bit. Here in this flowchart, I just want to extend it a little bit. If you just observe this part, okay, see this part here. Earlier I was just having this, but now I want to concretize the things, which means that if I'm saying there is always a solution, now I just want to say that okay, the solution will be unique or infinite, which means that I want to distinguish these two into two categories, whether the solution will be unique or infinite. So now if I just ask you whether the solution is unique or infinite, then you will say that okay, if the columns are linearly independent, then the solution is unique. If the columns are not linearly independent, then the solution is basically there are infinite solutions, which means if this B, whatever you are writing, if this B is a linear combination of columns of A, right, then you always have the solution first of all. But now the question is that, do you have multiple solutions or just one solution? It will depend whether these columns of A are linearly independent or linearly dependent. If linearly independent, then unique solution, or vice versa. I mean, unique solution means linearly independent. I mean, it's like a Y implication or something. Okay, unique solution means linearly independent, and infinite solution means that linearly independent, linearly dependent. Okay, so let's just see that why that is true. But before that, you should be understanding till this point, which means without this extension, you should be understanding till this point. So these two questions that we did, right, starting from these two questions that we did, this one, I mean, we had two variations, simple and then after the note. Similarly, this question and then after the note, right? So these two questions that we did, basically these two questions should be clear. Then we can just extend this idea a little bit. Okay, cool. Now let's just extend this idea in the next video, where I will just prove you that why this yes is having unique solution and why this no is having infinite solutions. Okay, so basically if the columns of A are linearly independent, then you will be having a linear solution if the solution exists basically, right? I mean, I'm assuming the solution exists, which means B is a linear combination of columns of A. If that's the case, yes, then I will say that okay, columns are linearly independent, then yes, then unique solution, otherwise infinite solution. If B is not a linear combination of columns of A, then there is never a solution. Okay, now you might say here that what if the columns are linearly independent? No, it doesn't matter. If let's suppose in R3 you have just two columns which are linearly independent, doesn't matter, right? You just have two linearly independent columns. But this B, whatever is given to me, this B is not a linear combination of columns of A, then you can never ever have the solution. Okay, cool. So let's just go to the next video to prove this extension. Okay, I hope till now at least the things are fine. Cool. Thank you so much.